Extremely Large Telescope is the largest optical telescope with a 40-meter diameter. It has 5 mirrors, 5,000 steel structure. It's amazing. It will look at the universe and we have great discoveries to come. We wanted also a sensor that had very low noise. The game changer when the Model S came out. And the Model S actually brought that level of noise to perfect value of 0.7 micro-G.
Wait, from 25
Yes.
to 0.7.
Yes, exactly.
Hi, we're here at the 2026 Dewesoft Measurement Conference, and I'm with Dr. Babak Sedghi, and he's with the European Southern Observatory, and he is one of the top finalists in the Engineering Excellence Awards. This year was incredible. He had an amazing application. I got to tell you the title of it, and then we're going to get into some of the details of what you did. So this paper was titled Structural Vibration Monitoring of Extremely Large Telescope using low noise MEMS sensors. So this had people fascinated, and I think you were in front of a lot of people who could really appreciate the incredible work you did. So give us a sense, first of all, about the Extremely Large Telescope. I think you mentioned it's the biggest in the world. Tell us a little bit about that.
Yes. Thank you very much, Dave. It's a pleasure to talk to you. Extremely Large Telescope is the largest optical telescope which is in construction in Chile. That is a telescope with a 40-meter diameter, the primary. It has 5 mirrors. It's a huge structure of 5,000 steel structure. And it's amazing. It will look at the universe and we have great discoveries to come. A lot of also unknowns, a lot of things that we know that we want to discover. But this telescope is started to be designed around 2008 and 9, and all the project advanced, and we are now on the construction phase. And it's we expect that to have the first light around 2030. And yes, it's an amazing project.
Yeah, so 2030, and I like the term first light.
Yes.
You'll receive the first light. Now, some of the things you have to worry about in this are vibrations, right, and characterizing all this. Tell us a little bit about some of the issues that you face and how vibrations affect this structure.
Exactly. So this largest telescope in the world, actually to get all these science cases that the astronomers, they want to achieve, actually, we need a measurement system, which is the telescope. It should be so accurate and sensitive. So a very small shaking and perturbation will hinder to get that objective. So there are different perturbations that are acting on the telescope. One is atmosphere. So it's a ground-based telescope. Right. So the light passes the atmosphere. And there are techniques actually called adaptive optics that they correct for the atmosphere. But also the telescope is constantly subjected to the other perturbation, the wind. But there are also other sources of vibration like machineries, pumps, that they have to be in the observatory, and they are affecting the motion of the telescope or stability of the structure. So the vibration is something that can happen at higher frequencies and also very difficult to control. So we are paying quite large attention to manage the vibration in the structure. And we started like 10 years ago to do a kind of systematic approach to do the modeling, simulation, and the structure itself and all the sources that are acting, and we think that will excite the structure of the telescope. And this is an iterative approach, and we are at the point that we have now kind of understanding about how this telescope will shake with everything that it will be installed on this structure. But one step is remaining, actually, is after all this separate measurement, characterization, and modeling, now is the time just to measure it on the real telescope.
So now you have the opportunity, as construction is going on, to put sensors out there, measure it on the real thing, and then validate the models and that type going forward. So it mentions MEMS sensors and low noise. And so you connect those, and there's a bunch of them, right?
Yes.
And you connect those up to measurement technologies like we have here today.
Exactly. What I wanted to mention earlier, I expressed the need to do modeling and measurement of the sources. So we, like 7 or 8 years ago, that was the starting point to use Dewesoft products.
Right.
So we had a serious data acquisition system, and we used that internally in our laboratories to characterize different sources of vibration. But now that we are going to measure the telescope structure itself, we need a different technology.
Right.
Because the structure is so huge, and first of all, we need a kind of network of the sensors that should be installed in different locations of telescope, sometimes with the distances of more than 100 meters. So we cannot use the classical data acquisition system with analog connection of different sensors going to different boxes. We need a system that it is scalable, and the product of Dewesoft Iolite 3 MEMS was actually satisfying that kind of requirements. So one of the interesting advantages of Dewesoft Iolite MEMS sensors is that the possibility of, first of all, having the DAC system, everything inside the sensor itself.
Right.
So the data actually coming out of the sensors were already digital. So we were less affected by the effect of the noise and all of these issues that can affect our measurements. I have to add also one point, that this large telescope, actually the structural modes is quite low, it's huge, it's heavy. So it is a very low frequency deforming structure. That requires that we need also the sensors that are capable to measure low frequency and quite accurately. And this is again another point, that Dewesoft Iolite MEMS sensor, they had a very low noise level at low frequency that actually enabled us to do this measurement.
This is incredible. So let's capture some of those points. Big structure. Did you say 100 meters distance?
Yes.
Think about that. So now you have to distribute all of these measurements over large areas, right? And then you're saying you put the sensors out there, but the digitization is done at the point of measurement.
Yes.
And then all that information gets collected back, and it's more immune to noise because it's digital, coming back. But this system has to be capable of doing time synchronization of all those measurements over these large distances.
Absolutely. You're touching a very important point, Dave, because what we want to also achieve is to combine all of this data real time and try to estimate the different deflections of this structure. So we want also to be able to measure at different mirrors the deformation and live movement of these mirrors and combine them. So you can imagine then a telescope with 5 mirrors, when it's observing, the light passes through all these mirrors. So the motion and shaking of each mirror contributes to that final image that we see on very sensitive sensors that we want to use and observe planets and stars. So we needed exactly synchronization of this data to be able to correctly combine all these data from different locations correctly, timely based. So this is again another point that again, I wrote it also in our paper, that is a perfect match, this system. Scalable, because we wanted also to start to this monitoring earlier stage of our project. So we wanted a system that can be scaled in time. We wanted, as you mentioned, a system that all the sensors are perfectly synchronized. We wanted also a sensor that had a very low noise. And the part of the noise actually was not happening 2 years ago. 2 years ago, these Iolite sensors, they had a noise floor of 25 micro G per square root of hertz. And Although very small, at that time, it was not enough for us.
Is that right? More sensitive than 25 microns?
The game changer when the Model S came out. And the Model S actually brought that level of noise to perfect, for us, the value of 0.7 micro-G per square root of hertz.
Wait, from 25?
25, yes.
To 0.7.
Yes, exactly. And that time, it was the time we said, okay, we had all our requirements, what we want, a scalable system, a system that synchronized. The data communication between these sensors are all digital. We can do a daisy chain of these signals. So connecting one sensor to the other with distances up to 100 meters.
So the fidelity of measurement, right?
Yes.
Scalable.
Yes.
Incredible.
Exactly. Yeah. All of this, when this happened, we decided, okay, we know it, let's go and start to do the measurement. And since we wanted to have this system phase-based, then we started to do this based on 9 sensors.
Okay.
And we had a mission last December where we brought these 9 sensors there, and we thought, okay, let's start to do this monitoring from the base. So from the base of the structure, and our plan was just go step by step up to the structure.
Up to the structure. So you have actually scaffolded up or progressed up the structure.
Exactly.
I see. So you mentioned low frequency,
yes,
but you need very, very high fidelity on those measurements. Does that mean you have a lot of data then, because you have to kind of wait a long time for a cycle to be captured?
Yes, and another interesting point that is very important is that for low frequency, actually we are combining, not only one sensor. So these are triaxial sensors, but at the area that we do the measurement, actually we place 3 sensors.
Wow.
So the combination of these 3 sensors and 3 axes for each sensor, we can actually reconstruct the 6 degrees of freedom of motion of places or areas that we want to observe the displacement or the motions.
6 degrees
of freedom.
Freedom.
Yes.
That makes for a fairly complicated model, complex model, would you say? Awesome.
Exactly.
So now you're collecting all this data in real time, scalable over large distances, very, very high accuracy measurements. And you're informing your models now on how to proceed. So what does this communicate or imply for you for the future?
Yes. Actually, one of the goals of these measurements is also to compare the results or the behavior of the structure with what we had at the beginning for the last 10 years in our model. So since now, as I mentioned earlier, that we have only 9 sensors and we are only measuring the pier of the telescope. The pier of the telescope, for information, is a concrete structure of 20,000 tons. And the telescope is above this, 5,000 tons, and we are only now measuring the deformation or the movement of the pier of the telescope. This large concrete structure is supported by 50 isolators. They call it also earthquake isolators of the structure.
Okay, right.
So, the Chile, where the telescope is installed, is a very seismic area. So a lot of seismic activities are happening.
Wow.
Also the large ones. So the telescope...
But clearer skies,
exactly,
right? I mean, you chose it for a reason, right?
Yes, absolutely. And yes, the safety of all the glasses and all the sensitive instruments during the earthquake is very important.
Yeah, it depends on this knowledge.
Yes. So at the moment, we could verify the models that model actually these 20,000 tons on these seismic devices. So there was a modeling, actually, what are the first eigenmodes and frequencies deformation of the whole telescope and pier on these devices. And the measurements that we had since December are demonstrating actually those modes and frequencies. And how we have the information about the frequency, because we have a natural shaking and shakers. These are all the seismic events that are happening. So now and then we see seismic events that they shake the structure, and all of these mechanical modes are shining out. And we see it live actually on the Dewesoft system.
Reminds me of the tap test where they tap something and they'd see the thing. You got the Earth tapping the telescope, and you're able to characterize it and see it all.
Absolutely.
All those modes
Yes.
reveal themselves.
Exactly.
Wow. It's incredible.
So this system was installed in December, and since then we are capturing live data. And for me it was quite emotional because, let's say, my goal was to put more sensors later on and then understand the structure of the telescope. Again, I repeat, we have not yet put any sensor on the structure. It's all about the base of the base.
Sure.
But I could not imagine that these sensors, so sensitive, and the system working so perfectly that already I have the information more than I expected. So December, and it was Christmas time, and it was new. I was looking at the data. You know, I wake up every morning, just putting the coffee machine on, and then also the system on, and looking at the data. Amazing. Yeah. And then sometimes some of these earthquakes were happening just live when I'm watching, and seeing all these mechanical modes that are appearing. I had a goosebump, Dave, because working on a project for 20 years, all, as you mentioned, simulation, all in the paper, 4 hertz mode, 5 hertz mode, you're talking all the time, and seeing it that actually the real system is doing that, and you see it for the first time. Yes. I say to myself, Babak, nobody have seen it before. Wow. And yeah, I was almost crying.
You know something? First of all, it's inspiring, and I totally get it, because I think about the telescope, and its job is to see clearly through the perturbation of the atmosphere out into space for clear images, right? But you're using this instrumentation to see clearly the nature and the motions of the base itself. So for you, the instrumentation created a different kind of telescope, in a sense, to clearly see what was happening, and you saw it. It wasn't theoretical at that point. You actually saw it.
Yes, that's true. Yeah,
incredible. It is amazing. Yes. Well, congratulations. You know, you're a top finalist, and this inspired a lot of people. Really, thank you.
Thank you very much
for sharing this information with us. Congratulations on the award, and we look forward to seeing how the images come from the telescope when we see first light. In 2030, I think you said, right?
Yes, yeah.
And we really, really enjoyed hearing about this. Congratulations.
Thank you very much, Dave.